If you've studied any heart physiology, you've probably heard of preload and afterload. And you were probably told something simple, like the preload is the volume in the ventricle, and that afterload is the pressure it pumps against. It's a handy shortcut that will even get you through a lot of exams, but it's not really what they are. Here's the story that gets usually taught. Preload is thought to be the end diastolic volume, so how full the ventricle gets right before it squeezes. Meanwhile, afterload is taught as the pressure in the aorta that the ventricle has to push against to get blood out. Both of these point at something real, but both quietly trade the true quantity for a picture that's easier to hold in your head. Because preload in reality isn't a volume, and afterload isn't a pressure. So if they're not a volume and a pressure, what are they? They're both a load on the heart wall, a force the muscle actually feels as it works, and the proper name for that is wall stress. So preload is the wall stress at the end of filling. It's the stretch sitting on the muscle just before it fires, while afterload is the wall stress the muscle has to overcome while it's ejecting. And the bridge that connects volume and pressure over the wall stress is an equation called the law of Laplace. And before looking at it, let's take a quick detour, because two words get thrown around here: tension and stress. They're similar, but not the same thing. Tension is the force per unit of length. It is the pull running along a line in the wall. So, the units are newtons per meter. While stress is the force per unit area. Same pull, but spread across how thick the wall is. And it is measured in pascals. So stress is really just tension, divided by wall thickness. But why fuss over it? The thing is, a thicker wall shares that same tension across more muscle. Same tension, but less stress on any one piece. For now, just hold on to that idea. It's going to explain something important later. So our goal for this video is to build an equation that lets us calculate the wall stress of a heart chamber. This equation is known as the law of Laplace. To build the equation, we need to define what stress is. It is defined as force over area, but the important thing is the way the force points. What is important is to know that any force on a surface can be split into two vectors. First vector is the normal stress, that the part of the force that pushes or pulls straight into the surface. And the second vector is the shear stress, which is the part of the force that pushes parallel to the surface. In our derivation, we'll only use the normal part. And now let's see why pressure and tension both act normal to the surface. But before that, I'd like to make an important note, that normal versus shear isn't fixed. It depends on which surface you're asking about. Change the surface, and the answer changes. For example, let's take a flat wall and apply some force to it. Let's imagine that that force represents blood pressure pushing straight on the wall it touches. So looking from the inner wall's perspective, pressure is pure normal force. But if we look at tension from that perspective, it runs along the wall, tangent to the surface, so it's shear. But that's a problem because we need both forces to be normal in order to balance them out. So let's try a different way. Let's take a surface that's inside the wall. On that fresh cut surface, the tension points perpendicular to the surface, so it's a normal force. But the pressure on that same cut pushes sideways. So from the cut's point of view, pressure is shear. So we are back at where we started. And on a flat wall, that's exactly right. Pressure there really is shear. So it could never balance the tension, since they point in different directions. So to solve this, we can use a curved wall, because the pressure there really stops being shear. The problem is that it only shows up once we add up multiple points. But let's leave that for the derivation part. So for now, take it as a promise. On a curved wall, pressure and tension are both normal to the cut, and that's what lets us balance them. Okay, now that we know the basics, let's derive the wall stress of a sphere. since it's a fair stand-in for a hard ventricle. First step is to slice the sphere in half, so we get something like a dome. But why would we do that? The reason is that in a whole sphere, all the forces cancel out and stay hidden, so keeping just one half lets us actually see the pressure and tension working in it. Okay, before continuing, let's review the plan. So our goal is to balance the force that is pushing the dome off with the force that is keeping it together. So let's start with the force that is pushing the dome away, which in our case would be the pressure inside the dome. So pressure is acting on the curved inside. So all those little arrows fan out in different directions. In order to balance it against the tension, each arrow has to become a vector pointing in the same way the tension pulls, because only then can we add them up. But first, we have to find those. So to do that, we can take any 2 points on opposite sides of the dome. We can see that their sideways components point in opposite directions, so we can cancel them. Every sideways component has a partner that kills it. Now we have to add all the remaining vectors together. But doing that with integration would be a nightmare, so we'll use a simple trick. But before doing that, I would like you to see that this is the answer we promised. Measured against our cut, the pressure shear part just canceled itself out. And now only the normal part is left. Now to the trick. The trick is that the integrated pressure on the curved surface is the same as the biggest pressure component times the flat circle the dome sits on. So that means that the messy curved dome and a simple flat disk feel the exact same outward push. The intuition for why curvature doesn't matter is that near the edge, the dome is tilted steeper, so it's pushing more sideways and less along the axis. But that steeper tilt comes with extra curved area, and the two effects exactly cancel. So we get more area, but aimed in a less useful direction. So to summarize this part, the curved surface pushes exactly like a flat disk of the same radius would. That's why we never integrate the messy dome. We just write that the force is equal to the pressure times the area of the disk. Now that we have the force that pushes the dome away, let's focus on the force that keeps it together. And that would be the tension created in the rim of the cut, which is quite easy to calculate because it's just tension times the circumference of the cut. Now we have both forces, so we can finally balance these two out. And we get that tension is equal to pressure times the radius over 2. But since we want the stress, we can just divide the whole of the equation by the wall thickness. And there it is. That's the stress law for a sphere. Now why should you care? Because that little equation is quietly running a lot of medicine. See that the radius sits right on top. That means bigger radius, bigger wall stress. For example, take a failing heart that's dilated. As radius grows, wall stress rises, even if the pressure hasn't changed. The muscle now burns more oxygen just to make the same beat. And that extra cost can drag a weak heart even further down. So it creates a vicious circle. It's also why we treat heart failure by unloading it. So by bringing down preload and afterload. You do that by shrinking radius and pressure, and with that you're reducing the wall stress. Same law also applies to different situations. For example, an aortic aneurysm. Having a wider vessel means more wall tension. So that means that the big aneurysms are the ones that are more likely to rupture. The law also explains hypertrophy. When the heart faces chronically high pressure, the wall will thicken. That's more H on the bottom of the equation. So wall stress drops back toward normal. The heart is literally solving its own equation. One last thing I want to mention are those shortcuts we started with. Those that see preload as volume and afterload as pressure. They're not really lies, and there's a good reason we teach them. We now know that wall stress is the real quantity, but you can't see it and you can't measure it directly. So instead, we use volume and pressure, which you can actually track and if needed change with a drug. So we trade a little bit of precision for something you can actually picture and actually act on. So in conclusion, preload and afterload were never really a volume and a pressure. Those are just the shortcuts we grab. Well, the equation is the machine that turns them into the thing the muscle genuinely feels, which is wall stress. So now we see that preload and afterload, heart failure and aneurysms, and hypertrophy are just one equation, seen from different sides.